Bases are a substance that dissociates in or reacts with water to form hydroxide ions. Again, it's a simple the initial definition, the Arrhenius definition. We'll get into Bronsted, Lowry, and Lewis definitions later in the semester. So a strong base, something like sodium hydroxide, as you can guess, is a strong electrolyte, and 100% disassociates or reacts to form hydroxide ion, OH minus. A weak base, i.e. something like ammonia, is a weak electrolyte. It partially disassociates or reacts to form OH minus. In the case of ammonia, it actually reacts with the water to, even though it doesn't have OH in it, it is highly likely to grab a hydrogen from water to produce hydroxide. So, for example, it's a classical strong bases, something like potassium hydroxide, dissolve it in water and it completely disassociates to potassium ion and hydroxide ion. As I was mentioning just before, ammonia, it reacts with water. It likes to pull a hydrogen off of water to produce the ammonium ion and OH minus. So here we produce hydroxide, not because the compound contains hydroxides, but because it reacts with water and one of the products is hydroxide. So it is also a base. Common acids and bases. So for strong acids and bases, basically the common strong bases are just any group 1A alkali metal with hydroxide. Rubidium, and cesium-OH are not nearly as common, but are also very strong bases. Ammonia is a common weak base. There are thousands and thousands of relatively weak bases, mostly organic nitrogen compounds like ammonia, but with like other stuff stuck on. If we're dealing with any of those, I'll let you know. For the strong bases, you should recognize which ones are strong bases. But the tests are open books, so I won't give you a table of strong bases, but it'll be open books, so you can look them up. For the strong acids, these are very common strong acids. Anything with a hydrogen and a halogen will be a strong acid, except for HF. We'll get into that later. Nitric acid, very strong. Sulfuric acid, perchloric acid, also strong. And then there's a whole lot of weak hydrofluoric acid. There we go, a weak acid. That's important to know, it's a weak acid. And then there's a lot of organic acids. There's just more that you can shake a stick at. And that's the sort of thing where, you should recognize, if I give a compound, I shouldn't have to tell you it's a strong base. A strong acid, you should say, oh, it's a strong acid. If you don't recognize it as a strong acid, it's probably a weak acid. Okay, so those are some common acids and bases. So what happens in the reaction? So neutralization reactions, let's take a look at this. So we can figure out the net ionic reaction by just looking at what's a strong electrolyte and what's a weak electrolyte. So what's the net ionic equation here? Let's start with the complete ionic equation. Well, KOH, that is a strong electrolyte. So we have K plus, I'm not going to write the in aqueous solution. Everything's here in aqueous solution. Nothing is going into gas or solid. OH minus plus HNO3, that's a strong acid as well. So we'd get H3O plus, because really it's in aqueous solution, so we can just pull waters from anywhere, and it is hydronium. Plus NO3 minus. All right, that's one side. The other side, we have potassium nitrate, which is definitely soluble by all of our solubility rules. So K plus NO3 minus plus H2O, because when we have H and OH reacting, that produces water. So that's our neutralization reaction. And we look at the potassiums cancel, the nitrics cancel, and what we get is OH minus plus H3O. And actually, H3O goes to H2O. We need to balance the equation. We added an H2O on the other side to make hydronium. To balance it, we have to put that here. So that is the balanced net ionic equation, which represents the ions that are actually doing the reacting. So when you mix a strong acid with a weak acid, like the chloride, the potassium and the nitrate have nothing to do with the reaction that's actually occurring. Once you put them in the water, they disassociate. They could care less what's going on. It's the hydronium and the hydroxide ions that are actually reacting. So it's sort of, ironic. We talk about hydrochloric acid, but it's really, the chloride is just along for the ride. It's the hydrogen that is the reactive part of hydrochloric acid. Hydrobromic acid, the same thing. The bromide's just chilling while all the reaction's actually happening. Its only job is to bring the hydrogen to the party. Okay, so if it's a strong acid and a strong base, the only reaction that's actually happening is OH minus plus H3O plus to produce 2H2O. Okay, what's the net ionic equation here? Well, KOH is strong plus HF. Aha, so HF is a weak electrolyte, a weak acid. The dominant species is just HF aqueous. It's a hydrogen fluoride covalently bonded, surrounded by water. It's not ionized. So that's the reaction here. And KF there, yeah, that is soluble. Potassium fluoride is soluble plus H2O. And so the net reaction here is what is a spectator ion is the potassium. The potassium doesn't want anything to do with this. It's doing its own thing, surrounded by water. It's having a good time. The reaction is OH minus plus HF reacts to produce fluorine plus H2O. In other words, the hydrogen reacts by moving from the fluorine to the hydroxide to produce fluoride ion and water. You notice I'm drawing like a double harpoon thing here to indicate there's actually some sort of, or a double-headed arrow to indicate some sort of chemical equilibrium. And we'll talk a lot more about chemical